Hello, everyone. Can you hear me? Give me a thumbs up because I'm also, I think, live streaming on YouTube. So there's a lot of audio and video streams. Give me a thumbs up if you can hear me. Hello, everyone. Can you hear me? Okay. Give me a thumbs up. All right. Thank you very much. And we get started in 1 minute. I also send a link to the YouTube live streaming. So in case if you drop out, could not join again, you can also watch it on YouTube. But that one is only 720p right now. I'm also recording the video, so I will post it on YouTube after the workshops. And so if you have any questions, feel free to drop in the chat. I will check it when I have time or during the break. All right, so let's get started. Welcome to the GeoAI workshop. So today we have 2 hours. So this is the first of the series. I'm hoping that we can do that more in the future, maybe bi-weekly or monthly, and depends on the feedback that I received today. I might do more in the future. And I sent a link in the chat to the GeoAI website, so you can click the link, go to the website. I'm going to show you step by step how to get to the notebook, and bear with me. I have 2 cameras, so I think this one right now I'm talking to Zoom and the other one on YouTube. And so if you have any questions at any time during the workshop, feel free to drop in the chat. I will check it from time to time. And so for this workshop, we have, I think, about 900 people register. So I think Zoom maxed out at 300. So you might not be able to join if you drop out later. I'm not quite sure. But again, the link to the YouTube is in the chat. So you can get a copy, or you can just go to my YouTube channel. And so first, I'm going to go through the notebook examples. I'm going to show you if you go to the opengeoai.org website, and then on the left side, click workshops, scroll down to find the last one, TNView 2025. So click the link. It will take you to this Jupyter notebook. I'm also going to send it in the chat here so that you can see it. You can click the link directly to go to the Jupyter notebook examples. And so this is part of the TNView webinar series. So TNView stands for Tennessee View. It's part of the America View network. So it's a network that's sponsored by the USGS. It's a national consortium of remote sensing scientists and educators. And so I'm the PI for the Tennessee View. Our mission is to advance geospatial research and education. So this is part of the training that open for everyone. So I hope you're going to learn something useful. And before we get started, I would like to have a brief audience survey. So let me see if we can. This is the first time I'm doing that, so bear with me. I'm going to launch the audience survey. So you should have received a pop-up in your screen asking you about some 5 simple questions. So I would like to know what's your background? Do you have any deep learning background? So during the workshop, I can focus more on some basics or more advanced topics, depends on the audience response. So feel free to just ask answer those questions, and I will share the result once we're done. So I give you another minute. And thank you for those who have responded. We have 172 people right now. So okay, 67%. So we have maybe another 30% of people that if you can respond, that would be great. And I will share the result maybe in 20 seconds. Okay, we are at 80% now. Okay, we have 84%. I think we can just go ahead and end the poll. And so we can share the result. You may be able to see the result on your screen. I'm going to also share here. I think we have a lot of students, some faculty, and also some from industry, kind of very even. That's great. And many of you already have some GS background and with desktop GS. That's great. So we're going to make it easy to understand some of the concepts and the imagery. In terms of AI and machine learning, some of you have the basic, intermediate. That's also great. If you don't have any background, that's fine. Don't worry. We're going to start from the scratch. So as long as you have internet access, you can click the buttons. You'll be fine. So trust me. And in terms of the GeoAI package, only 60% have used. More than 84% have not used. So hopefully after today, you'll be convinced to use it in your daily workflow. What do you want to gain from this workshop? Learning the fundamentals of GeoAI, hands-on, real applications. That's awesome. So that's all we want to cover in today's workshop. And so let me stop the sharing right now. Oh, I can share the results. Okay. Anyway, so let's get started. So let me go back to the notebook example here. Again, I've linked in the chat, so feel free to click the link. And anytime during the workshop, if you see any issues with the audio or the video, just drop me in the chat so that I can see. And I will check it from time to time. And the workshop is being recorded, so don't worry if you miss some parts of it. I will upload it to YouTube after the workshops and later today. And so for today, we're going to cover a lot of practical examples. You can go through the notebook right now. It's a pretty lengthy document. We will try to cover all of them. If we don't have enough time to finish all of them, that's fine. So we have 2 hours. We should be able to cover most of those. And so there are 2 ways you can follow through. I would highly encourage you to follow me and then run the call and then get the results, see the result, change some settings, and then experiments. Do some experiments if you can. And so the easiest way for those that haven't used GeoAI before, I mean, the easiest way is to using Google Colab. It has some free GPU. So for now, you can just click the link here, right-click, open in Google Colab. Okay, and we're going to use the GPU. So let me also send the link in the chat. You can click that directly if you want to. And so once you're here, the first step is to click this runtime in the top menu here. Make sure you click this one and then change runtime type. Okay, so make sure you click this button, change the menu, change runtime type, and then switch to T4 GPU. Okay, if you don't use GPU, it's going to be very, very slow. So switch to T4 GPU and then just click save. Then you should be good to go. After that, just scroll down. You cannot see my screen. Anybody else can see my screen? I think I'm sharing the screen. I can see that from YouTube. Okay. I mean, just yeah. Okay, everyone says fine. That's you might need to restart your Zoom. So just click change settings and then change to T4 GPU. Scroll down to find this code block. It says pip install. Just control slash to uncommon. So control slash on your keyboard, or you can just manually remove this hashtag at the beginning and then click run anyway. Make sure you log into your Google account, otherwise you may not be able to use it. Okay. Don't worry about the content. I will go back to introduce it later, because installing the packages and also training the model might take a couple of minutes. So I want you to run that while we are waiting. I can explain all the concepts about deep learning. So just wait until it's done. Hopefully, in maybe less than a minute, you should be able to see that it's safely installed. Then you should be good to go. The link to the notebook, let me paste. Okay, you can also find it on the Open GeoAI website. All right, so we have finished the installation. Now I can scroll back to here. I would suggest that you just clear the selected output, because it's quite lengthy, taking the space. So click this one here on this button, click selected output, then you should be good to go. And then after that, it's pretty simple. All you need to do is just click the button, follow through. And I will show you some of the best practices. Also, how do you deal with the errors later when you run into, because on the right here, one thing I wanted to open is to click upper right corner here. It says RAM disk. Click the button. And from here, you will see the system, the memory, the GPU, and also the disk, basically the hard drive. So what you need to pay attention is to the one in the middle. So this Google Colab GPU has 15 gigabyte. It's pretty decent. It's better than most of your laptop. Most people probably don't have the GPU, and it's 15 gig. It's okay for most of the examples in this notebook. Not every examples. You will run into errors. Trust me, but that's fine. Don't worry. The workflow is the same. So if you run into errors, all you need to do is just runtime, restart section. So restart the section. And then you don't need to reinstall the package again. So for here, you can just control slash to comment it out, because for the installation is one time only. You don't need to install multiple times. For the other source code, you need to do that. You need to rerun it. So for here right now, just import GeoAI, and it will take a couple seconds. Once you're done, then you can start running through the examples. So here you will see it's pretty simple. You don't need to import 20 packages, just one. And that's pretty much it. It's very simple and easy to get started. And so in the middle here, you see the GPU RAM. This one is not being used right now. So because we haven't loading the data into a GPU yet, and just wait for this one to finish. Okay, it's done, 28 seconds. It's a little bit longer than I expected, but so next, just click run these examples right now. Run these two code blocks to download the sample data, and then I'll go back to explain the basic, because training the model is going to take some time, 5 to 10 minutes. And because we have right now almost 200 people joining, I don't know if you got Google Colab going to limit the GPU usage or not. But then scroll down to find this one. Okay, so this code block is training the model. It's going to take a couple minutes. So just run this one and that run. And if you run into errors, let me know. Otherwise, you will see here on the right, it's going to start seeing the GPU usage spikes, because it's loading the data into GPU, start doing the training. Is there command in VS Code to enable GPU? No. If you don't have a GPU locally, then the easiest way is to try Google Colab, okay? Because locally, if you don't have GPU, even if you have installed the package, it's going to be very slow. So just use the link that I sent. On the right here, right now, see the GPU RAM, 36 gigabyte, and you will start seeing the yellow. That means it's like close to the peak. So, and then it might flash out at the red color. But I've tested examples; it works fine. So it just takes a couple minutes. So just be patient. But if you run into errors, then just restart the section and then run import the package again and then run over. So you should be fine. And so this is pretty much it. Also, I would like to point out on the left side here, if you click this hamburger icon here, the same icon here, on the left side, you will see the table content. So we have a lot of practical examples. So if anytime that you want to navigate through, you can click just navigate through to see different sections. So right now we're running the first one, and so we're going to let it run. So for now, I'm going to go back to the beginning, and I'm going to start running it on my local machine so that it's much faster. But you will continue to use Google Colab unless you have a GPU and also you have installed the package on a computer. So this is right now I'm running in a Jupyter notebook on my local computer. And first, I'm going to go to the very beginning. So what exactly is GeoAI? Okay, so GeoAI is a term like geospatial for artificial intelligence. But what we're talking about here, GeoAI today, is a very native one. It means the Python package called GeoAI. And you can use it to do all kind of deep learning and machine learning with geospatial data. So the link, if you go to the website here, GeoAI, opengeoai.org. So this is a package that I created actually 2 years ago, but I didn't have time to actually develop until 2 months ago. So the package actually, most of the functionality that we are going to try today is pretty new. So it's 1 or 2 months ago. So, and it's still under active development. So you can check out the website, or you can go to the GitHub webpage here. I would appreciate if you just bookmark your start the GitHub if you have a GitHub account, so that you can get the latest update for all the development. And the package is open source. You can look at the source code. I welcome your contribution. So if you want to receive the update, then you can start the repo or watch the repo, so you get latest information about the features that I have been adding to the package. And so you can go through the website if you want to. Also the installation, if you want to try it out on your local computer, you can install using pip or using Conda. And if you have a GPU on your computer, then you might want to use the PyTorch CUDA version, so the training will be much faster. Earlier, when we installed the package on Google Colab, because Google Colab, we use the GPU runtime, so it's actually installing all the GPU, PyTorch GPU, so that we can utilize the GPU. And on the left side here, you will find a lot of examples. I don't remember how many of that right now, maybe 40, 50 examples. So for today, we're going to cover maybe just 5 to 6 examples, but you're welcome to check out every notebook here. And also the workshop, I've switched workshop so far, so I'm going to use the TNView, this one today. And you can also look at the API document, basically for all the functionalities. If you click, you'll be able to see all the functions for each package. And then if you click here, you'll be able to see the source code. So every function, the source code for every function is also available there. So this is kind of the website. You're welcome to explore after the workshop. So let me go back to the notebook here. And there's a question about the UV. UV basically is a drop-in replacement for pip, and it's much faster. I would recommend if you want, you can install UV, but in this case, I would recommend using Conda, because UV doesn't really handle the GPU installation very well. So if you have GPU, then Conda is a better one, because it already compile all the packages. So it's less likely going to run into GPU package installation issues. But certainly, if you're comfortable, then you can use UV to install all the packages. All right, and get back to the notebook examples. So for today, I'm going to cover some of the key functionalities. So the GeoAI package has some of these key functionalities: data pre-processing or data download. So once you download the data, we can process the data into image chips, and then we can do the model training. So using the image chip to do the training, and then we can run the inference on the data. And after that, you can visualize the data, either the result or the original data. Right now, if you don't understand some of the concepts here, that's fine. Don't worry. Once you get into hands-on, then you will understand basically the uses of those functionalities. Also, there are some additional resources. Again, you can check out the GitHub repo. Again, you can start the repo if you want to learn more. Right now, I think it's 1,000 400. So if we can get to 2,000, that would be great. Next, there's also a book. So I published a book 2 months ago during the summer. So this is more, it doesn't cover GeoAI, but if you're new to GeoAI, you will need some Python programming knowledge. So if you are new to Python programming, this is a book that you might want to see. All the code examples, they are all open access. So you can download the notebook example, you can clone the GitHub repo, you can run the code example. So it covers a lot of packages, most popular one, and also some of the ones that I developed, including Gmap, LeafMap, and some other packages. So you can try it out if you want to. If you want to support me, you can buy a copy from Amazon. So I'm going to send the link here if you're interested in. So these are all free open resources. So the book is available on hard copy on Amazon and also PDF copy with, I think, over 10 translations. So for the English version, it's available here on LeanPub. So I try to make it as affordable as possible. You're welcome to purchase it if you want to support me, but you don't have to. There's all the notebook examples are freely accessible. So just the text and also the images, figures are not available here. And also, there's a video tutorial. So here is the entire video tutorial series. So this is the one that I teach at the University of Tennessee, I think last year, 1 year ago, and it covers all the content. Of course, the books cover a lot more. So this is only week 14. I think the book has over 20 chapters. So there are a lot more information covered in the book. But if you are new, there's some of the video you can check out. And the other one I want to quickly mention is the GeoAI tutorial series. So if you go to my YouTube channel here, oops, not this one. So if you go to my YouTube channel, there's also a series about GeoAI. So this is the one that's very relevant to what we are talking about. So far I have created 25 videos, and each one 10, 15 minutes. So introduce you how to use the package. But this workshop is going to cover most of the key workflows, so you don't have to go watch all of them if you don't have time. And lastly, so if you want to learn more about some of my other open source projects, you can go to the Open Geospatial Solutions. So I have many other packages. GeoAI is just one of them. I also created a second geospatial, LeafMap, Gmap, some other packages. So I welcome a contribution. If you know how to contribute, please feel free to submit a pull request on GitHub or raise issues. The more people use it, the better it's going to become, because I receive the feedback, I can improve it, other people can improve it. So thank you for your contribution. So next, let's get back to the, okay, the notebook actually is done. That's great. So right now, I recommend that you maybe go to the next step, because if the notebook is idle for too long, and then it might disconnect. So right now, if you can, just go to the next block and then we come back later. So in that way, the notebook is active. And I'm gonna go back to explain some of the concepts. So for GeoAI, basically is a package for doing AI with geospatial data. So AI, deep learning is part of the AI, right? So deep learning is also part of the machine learning. And so specifically for today, we're going to cover some of the basic concepts, including the model architecture, the encoder, the decoder. You will see some of the analysis in here, and these are some of the basic description. You can ask ChatGPT or any large language models to help you understand some of those concepts. So this text actually from AI. So we are doing GeoAI, so we also need to use AI. And just to give you an analogy, what exactly is the kind of model architecture? Because later when we start doing the deep learning, you need to select, okay, what architecture you're going to use, what kind of encoder you're going to use, or what kind of model weights you're going to use. So you can think about the architecture as just kind of the blueprint. Imagine you are the car, for example, the production, right? So how to actually produce a car, right? You need to have all those materials, and then to generate the glasses, the window, and the door and everything, right? So from the raw material, eventually to come out as the product of the car. There are lots of process. So the entire process, you can think about that is kind of the model architecture from the beginning to from the input to the output, right? The whole process is kind of model architecture. So the model architecture has so many data layers, right? So you can produce the glasses first, and then you can assemble, and then you can check the engine and all the stuff. So that one is the model architecture. in terms of the encoder is the one actually you can think about is just part of the molecule architecture. It's a part of the assembly line, right? So you can think about if you're doing the digitization, right? So the whole process doing digitization, you can have a camera, you can take the photo, and then the photo is being uploaded to the phone, to the cloud, and then it's going to do maybe just do the scan the PDF, the images, and then to recognize all the text or something like that. So a singular encoder is basically taking the input and then generate some compact representations of the imagery. So sometimes it's also called the result is called the embedding. So once you generate the encoder, so you turn it into numbers, basically the encoder, and then it's passing the encoder, and eventually you have a decoder to actually change it back to the product. And so think about the model architecture, the input, and then the encoders, and then from the encoder to the decoders at the end. So in terms of architectures, there are multiple types, right? So we have CNN, we have transformers. So transformer mostly is for large language models, ChatGPT, Gemini, something like that. And we also have the CNN. So for today, we're going to focus on this one because for geospatial data, we have a lot of images. So for CNN, it's very popular for processing satellite imagery. And you can learn, read all the text later. So for the encoder, transformer encoder, something like that. So it's taking the input and then generate the so-called feature representation in terms of just numbers. So it's think about it as a black box. Inside that, it has locked numbers. So if you give me input, I will give you some output. And then this output eventually can pass into the decoder to generate, for example, the final lane cover classification. We have some of the practical examples to show you later. And in terms of architecture, there are some of the options in here. I would like to give you an analogy. So think about if you need to do something, you want to use ChatGPT or Gemini or Clock or whatever you want to use, right? So the architecture you can think about is one of those, right? So one of the large language models. And then inside large language model, they use some transformer encoders to actually understand your questions. And then the computer only understands 0 and 1. It doesn't understand your text or the question you are asking. So it's turning your questions into some numbers. And then that number is being understood by the model, and then they can process it. They can give it a result. So here, for this one, for today, we're going to focus on image segmentation and classification. So there are some of the popular model architectures. You can click the link here, take you to the PyTorch segmentation model. So this is one of the popular one that we're going to use. You can also check out their website here. I will show you later. Right. So these are some of the basically model architectures, right? UNet, DeepLab, and some others. Also, there's so-called available encoders. I'm going to show you here. If you click this available encoders, then you're going to show you basically the table. So this is the ones like what kind of things to choose. This is where you need to decide which one you're going to use. So you can try. It depends on your GPU capacity. You can choose a large one if you have more GPU. If you can choose a smaller one, you can see the pre-trained weight. So the encoder basically you can think about is a model. Give me input, I'm going to process and give you the output. And the pre-trained weight is that you don't want to start from scratch because it takes time. So pre-trained weight means we can do this is so-called the transfer learning. So if you're trying to basically extract buildings, for example, right? So if a human, like when we see it, extract the buildings, then we see the edges, we see the color, we see the texture. But some of the things are very common compared to identify cats and dogs, right? So because those things basically are the edges, the pages, or something like that. So we use some of those pre-trained weights that have been trained by other models. And we can use this one just to do a little bit fine tuning. Then we become new weights rather than we have to start from scratch. And we see the number of parameters here. The larger the parameters, the more GPU you're going to use. So similar to some of the large language models, for example, a Llama 3.1, 4.0, right? So we are getting more and more larger and larger models. You need more and more computational resources. But for today, we're going to use some, for example, UNet and ResNet 34. It's pretty small that we can use the GPU in Google Colab. Okay, by the way, so let me go back to here. If you can just run another code block, because if it's idle for too long, then you will disconnect. So just run a code block, then we can go back to explain the concept. And yes, the notebook is available on the website. It's already posted, so let me send the link again here. And yeah, so that's pretty much it. And so the architectures with different options. For encoder, we also have different options here. And so all you need to do is okay, choose the best one or the one suitable for your task. If you don't know, you can ask ChatGPT like, I want to do this task. What kind of model architecture is best suitable for my task, or what kind of encoder? And if they're already available here in the PyTorch segmentation models, then later I can show you how to customize it. So all you need to figure out the workflow and where to change it. That's it. Only a couple lines of code. You'll be able to do the deep learning by yourself using your own computer or Google Colab. All right, so that's all about the introduction. Again, I don't have time to get into the technical details of everything, but this kind of the big picture overview, like what exactly the deep learning. So basically, there's a whole model architecture, and inside the architecture, there are different data layers, that different process, and then so for each one, there's some kind of encoder to read your data and then transform your data into some kind of numbers that can be understood by the model. And then you're going to generate the output, and then it's passed into the next step. And then eventually, is to come out using the decoder, is to change your numbers back to something you want, back to, for example, length cover classification, segmentation, or regression, or something like that. So now let's get started with the hands-on. So how do we actually utilize the package to do deep learning? So we have a couple examples. I'm going to show you here on the left side. You can take a look. We're going to show you how to do the segments, for example, surface water with non-geospatial satellite imagery. A non-georeference, that means it can be JPEG or PNG. So those are some of the formats that commonly used by computer vision. So they might already created some training data, the label and the mask, and then so the imagery. It's just JPEGs that has no geo information. So it's very common use case. The second one is about Sentinel-2. So it's real satellite data, real geo-reference imagery. It can be Landsat. You can customize to Landsat as well. So we have multi-spectral data, for example, 6 spectral band. We're going to basically use that to do change the data model and then do the segmentation. We also cover area imagery. For example, if you have high resolution area imagery, in the US, we have national coverage from the USDA National Agriculture Imagery Program that allows us to get the sub-meter resolution satellite imagery. And also, we're going to talk about, for example, building detection, and also with LiDAR data, and also, for example, solar panels. So we're going to cover a variety of use cases from non-georeference imagery, PNG, JPEG, to satellite imagery, 10-meter resolution, medium resolution, to high resolution, fine resolution, area imagery, drone imagery, and LiDAR data. And then we're going to show you different applications. It can be surface water, it can be building, it can be anything else, any feature you want to detect. So this is what I'm going to cover today. And let's get our hands on the source code, on the example. So if you just follow it in the Google Colab, so I'm going to run it on my local Jupyter lab here. And like I said, I'm going to scroll down to the example. So for the first example, we're going to use the water body dataset. So this is the one from Kaggle. Credit to the authors, Francis Sixcoat, for sharing the data. So if you see, click the dataset here, it has images and also the mask, 2,841. So these are all the JPEG of the dataset, and you can take a look at that. So we have basically, it has the images, it also has the label. And I also have a copy here on my computer. Let me see if we can. All right, so it doesn't show me the, my taskbar is hidden, so it doesn't come up. Let's see here. Interesting. Anyway, I will show you later. So let me go back to the example here. I have downloaded a copy and then put it on Hugging Face, because Kaggle, you need to log in and it's a little bit slow. So I have downloaded the copy and then put it on Hugging Face. So all you need to do is just use the GeoAI package to download the dataset, and it should be downloaded and then unzip. If you on Google Colab, you can find the dataset here on the left side. It should be downloaded, and you can click water data set, and then images and mass. Okay, the unit models is the one that we already trained. So don't look at it right now. So you can see the images, water body 1 all the way to 2,861 images. Also have the mass. So the mass basically is just the binary mass, water mass. And let me show you what it looks like here. Oh, let me train the model first, and then I'll show you, explain some of the key parameters. So that's it. So take a look, right? We basically, what you need to do, what you need to have is something like this. Okay, so you have a folder of images. It doesn't matter how many images you have, and also you have a folder of mask. So they are corresponding relationship 1-to-1. So you have one imagery, you have one mask, and so you should try to make the file names consistent. So otherwise, they don't match each other. That's not going to be good. And so once you have this, let me see if we can open the. Yeah, right now I don't see. Create a new folder. Okay, so now I should be able to open my. Oops, not this one. Bear with me. Let me because I hide my taskbar. So right now, I think Zoom blocked the change here. No closer. Open. Okay, so hopefully I can open my browser. Yes, okay, so now I have this. And let me show you here on my computer. This is data set that I downloaded it, right? So we have all the images. You can see the water body, one JPEG, right? So this is just a common set of imagery, but it's a JPEG without geo reference information. And for each imagery, it has the corresponding mask, right? So if you see, this is the mask for that particular imagery. If I go back to this one here, right? So they're one-to-one, so they make it's an image pair, and you can go through all the examples, the same workflow. Oops, here. So actually, let me send this one. Anyway, I will come back later. So this is basically the image we're going to use to train the model. And next, let me show you some of the key parameters that you need to customize. So if you look at this one line of code, so this is the code that you use to train the model. So you have the data, and you have the imagery, you have the mask. So what I need to do here is to just specify the input folder. The output folder here, we already set the output, right? So when the output to basically this water data set. So this one is the output data set. So it's basically download to this one and then save to the output directory, unzip the directory. And so what we're going to do is to save the result under this one, the unit models. If you already run the Google Colab, you should see this one here on the Google Colab here. So this is the model that has been trained. The result will be saved here. And so these are basically the input and the output. The next one is the model architecture. So this is where you actually customize it. And so depends on your task. You can change different model architecture. It can be unit, it can be other types. Like I said, you can click the link here, take you to this one. So these are all the model architectures available. So you can use ResNet, not this one, not the encoder. The segmentation models here, right? UNet plus, and deep lab, whatever, right? So you can try out different models. And in terms of the encoder, this is basically on the left side here, available encoder. So we can use a combination. So you can change, you can use any encoder here. For this particular example, we're going to use ResNet 34. But if you don't have a large GPU, not enough, you can use a smaller one, or you can try out a larger one. So usually the larger, should be a little bit better, but not always. But you will need a lot more GPU. And the image weight is using the ImageNet. So this is basically the pre-trained weights that have been trained on some other data set, but it's not trained on geospatial data. So this is so-called transfer learning. We can use those trained weights and then apply to our task, and then we train our model. It's going to basically convert much faster. So this is going to save you time. Otherwise, if you start from scratch, it's going to take some time. And then the number of channels. Number of channels is how many bands in your imagery. So this is non-geospatial data because it's just JPEG, usually it's just RGB. So the channel here is going to be 3. But later, when we use satellite data, then you have multi-spectral bands. You can customize this one to any number of channels, right? So right now we only have 3 channels. And number of classes. So number of classes, in this case, we are trying to do water mapping. So we have water and non-water. That means there's 2 classes. But if you're doing land cover classification, then you do multiple classes. So it can be tree, it can be vegetation, it can be water, it can be others. Then you change this number to whatever the number of classes you have, including the background. So the background is the class that doesn't have anything. So that one usually is going to be 0. So make sure here the class is not 1. Okay, is minimum it should be 2. It's the foreground and the background. The foreground is any object you want to detect. But if you have other classes, then you have more. So for today, we're going to focus on image segmentation, object detection. Usually only have 2 classes, but in a future webinar, we can cover more like multi-classes, but the workflow is pretty much similar. Okay, so that's about the classes, and then batch size. Again, okay, from time to time, go back to the notebook, because I'm at the beginning, I'm explaining the concept, so you take a little bit longer. So try to run some of those so that your notebook is not idle, not get disconnected. I'm running locally, so I don't have that problem. So next, batch size. So think about here, we have 2,000. Let me open this one again. We have 2,861 images. So let me open the folder here again. And so this is pretty big. So if you select all the images, right? So this one has 161. So there are a lot of images. And for doing deep learning, we don't want to feed all the images all at once into the model, into the GPU, because your GPU might not be big enough to feed all the images all at once. So the batch size basically means like you can subdivide into smaller batches. So each time I feed 16 into the model, 16 into the model. So 16 into the model, and then it's going to be retrained and then give some initial parameters, and then feed another 16. Then it's going to basically back and forth. So it's a lot of iterations to figure out what are the parameters, what are the weights that will be optimal for your model. So 16, basically how many epochs. So epochs means finish all the images. So that means for each epoch, how many batches you want to have. So you just divided 2,861 divided by 16. That means how many batches, okay? So one epoch contains multiple batches. So that means like eventually loops through all the images. That's one epoch. And then you can have another epoch. They do that again, because each time for each images, for example, 16, each time is random. So it's a random process. That means the first time you're going to get 16 images, it's not by sequence. So get 16 images, dump into the model, and then train another 16, dump into the model. And once you have finished all the 2,841 images, then you are done with one epoch, and you do again. So in general, this is the lengthy process. So the number of epochs, right now I only put 3. It's not enough because it's going to take a long time. You're doing Google Colab. So for me, for example, I can change to maybe, how about, you will see here, I only train like 3 epochs. You will see all the result in here, but I can change it to maybe, change to 10, for example. Usually you want to train 20 to 50 epochs just to be safe, but sometimes if it's just 5 epochs, it's already fine. And you will see right now here, I'm training the model, and you will see how long does it take compare. I can also monitor my GPU, so that you know how much GPU is being utilized. So I can maybe run this one here. So you can see on the right now the GPU is being utilized. So I have 2 RTX 6000 GPU, 48 gigabyte each, and you see it's actually utilizing 2 GPU. If you look at the text, use 2 GPU for training. If you go back to Google Colab, scroll up to the top here, and this one is actually just using 1 GPU, and take a look how long does it take. So for each time, for each batch, it's taking roughly 10 seconds. Because I have a larger GPU, and each one is only taking less than 1 second. So you can see the speed is like 10 times difference. And this is why like it's computationally intensive. So the larger the GPU you have, the better, the faster you're going to get. So for me, even if I train 10 epochs, it's probably faster than you train 3 epochs on Colab. So I just want to show you like the result. If you run a Google Colab for 3 epochs, the result is not going to be very good. So you will need to basically train a little bit longer so that you have better results. And so once you're done with training, you will see the GPU actually drop to a lower percentage because the GPU is only being utilized when you are training the model. So you are feeding all the images into the model, it's doing the training, and then go on and on until you finish all the epochs, okay? And the other one I have to mention here is some of these metrics, okay? Training loss, validation loss, and validation IOU and validation dice. You can take a look at some of the things in here. Learning rate, 0.0001, and also validation split, 0.2. That means we're going to use 0.2 means 80% for training, 20% for validation. So you can think about we have 2,800 images, 80% of those we're going to receive randomly selected, passing to the model. And then the reason why the model can optimize is because we have 20% for validation. So once you train the model, you're going to use that one to run the prediction, run the inference on the validation data. So the validation loss is the one that's guiding the training process. So if the validation becomes very bad, it's going to go back. So think about here, the learning rate is also a parameter that can control how fast you want it to converge. Imagine you are at the top of the mountain and you are going to go to the ground under the mountain at the foot of the mountain. Then there might be multiple pathways to get there. You might have a straight path, but that one might be very steep. Sometimes if the learning rate is like very high, it's going to take a long time to because you can think about you might fall down somewhere and then you need to maybe go to the other route. So the larger the learning rate, that means you are more ambitious, but sometimes it might be too much. Okay, if you have a lower number, then you are more conservative. You work slowly, although it might take a longer time, but it's more safer. So in general, you can use 0.01, 0.1 or something like that. You can play with it. So for this one, we just use 0.01. That means we're going to basically slowly decrease the, you can think about the training loss. It's going to fluctuate quite a lot, okay? And if the larger number, it might fluctuate. Sometimes it's way too much. But this one here, we use 0.01 and we train 10 epochs. Target size is 512 by 512. So the target size is like, sometimes we have images that with variable size. For example, the images that we have in here, most of these are 512 by 512. So it's already organizing a standard size. That's great. But sometimes you might have images with different size, 1024, something like that. Then the model we need to basically, because when you are training the model, we need the standard size. So that's why we have the, basically it's going to rescale them to 512 by 512 or maybe crop the imagery, rotate the imagery. So these are some of the things that but in general, you can leave it as default. You don't have to worry about that. The model will take care of that. So it doesn't matter what images size that you provide. This one, you don't really need to set unless it depends on the object you want to detect. So think about here, if you're trying to detect large infrastructures, then in general, the target size should be larger than the feature you're going to detect, okay? Otherwise, you're only seeing a parcel of the building. So if you have very large buildings, it is larger than 512, then you want to change this target size to be a large one. So make sure that the target size at least can contain the entire object you want to detect. So for the smaller, the faster, the larger, that means the more GPU. So think about here, each time we are putting 16 images into the GPU. So the larger the size, the more GPU. If the smaller, that means you might not be able to detect large objects. So this is something that you need to consider. And the last one, variables, is whether you want to see this the logs or not. And in general, what you need to pay attention is the training loss, validation IOU. IOU basically means the intersection over union. So the dice basically is just the F1 score, but I will get into that later. So after you finish the training, you should be able to find the these four outputs from the training model. So the base model, .pts, final model, and the training history, and also the training summary. What you need to know is the base model is the one with the highest IOU, okay? And the final model is the one finished. For example, we have 10 epochs, is the one at the end of the training process. So these are the two files that we're going to utilize. In general, we use the base model. And the training history is basically record all the loss. So this is the one we use to evaluate the model. So right now, if I run this one, you will see it looks like this. So this is basically the graph. Oh, by the way, so we finished training. So on the right here, you see right now the GPU is not being utilized anymore. So you will see the graph like this. Again, if you go back to the notebook, then if you run this one again, because I only trained 3 epochs, so it looks like this. It's normal. I see a demo here. This one I trained, for example, 50 epochs. So what you're looking for is that in terms of the loss, it should be decreasing, right? So we have 50 epochs, and you see, right? So the train loss is decreasing pretty nicely, but for the validation loss, it actually fluctuates. This is normal. So this is exactly the same as traditional machine learning imagery, remote sensing, for example, classification with machine learning, because the training loss usually is just go like decrease very quickly. But in terms of validation, is once you train the model, you're going to apply that to real images. So sometimes you might basically overestimate or underestimate it. So eventually you're going to basically fluctuate at the beginning quite significantly, but you should look at the trend that overall is actually converged. You're going to decrease. The overall trend should be decreasing. If it's not decreasing, something is wrong with the model. That means you need to change the model architecture or something else. The second one is the IOU. IOU basically means the intersection over union. And so basically it means basically the force is, you can see here, the area overlap. So think about, okay, this is the building already detect, right? So this is the ground truth, and this is the basically the prediction. So the overlap between your ground truth and prediction is the IOU. So it's a very simple matrix. And in general, you want to target at least 0.7, 0.8. So the higher the better. The value range from 0 to 1. So 1 means is that your prediction is exactly the same as the ground truth. That's a perfect model. And the 0, that means it's random. That's not useful at all. And there's also a F1 score or the dice. That means this one basically is more similar to IOU, but in general, it's higher than the IOU. So it's basically kind of more flexible, because the IOU is very strict about the overlap. And the F1 score in general is a little bit higher, because the IOU penalized for small mismatches, less forgiving, but the F1 score is a little bit more forgiving. So that means in general, you will see the value here is slightly higher. So in general, if you look at the train log here, 0.61, the other one 0.72. So sometimes you need to focus on like small, you can just look at the IOU or sometimes look at this one, but in general, you can use one of those. So you will see overall is actually decreasing the loss, and the IOU and the dice score should be increasing. So, and this is what we are looking for. This is the training you should be looking for. So after you finish that, this is the file training history.pts. That's the one that contains all the training history. Okay, and then we have the model. Then that's it. So you can think about here how many lines of code that we have. It's basically 1 line of code to do the training, and then 1 line of code to evaluate the model, and then 1 line of code to run the inference. That's it. Of course, you need to prepare the data, specify the way the input, and that's it. So you don't really have to worry about the traditional deep learning workflow. Prepare the data set, data loader, data set, and then chain all the things together. That's like 1 line of code at least. But right now we simplify into just a couple lines of code, train the model, and then we can run the inference. So let me see if there are any question here that I need to address right now. Does the image sample for 80% change on each epoch? No, 80% is always the same. So for each epoch, I'm going to get 80% of the images, and then each time I select 16, and then for each page, and then once you finish all the images, then it's 1 epoch. So each time for each epoch is 80% for training, 20% for testing. And this is exactly why you see this one here, right? So for example, in the first epoch, right? So you have the training loss, and then for this one, it's going to fluctuate because the image is random. So each time 80% of the images are randomly selected to train the model. How does the image resolution affect the selection of target size? Good question. So the target size is basically how many pixels, and depends on the feature you want to detect. So in general, for example, they say I want to detect a building. So in general, the building may be let's think about the size may be 20 meter by 20 meter, for example. So if your image is 1 meter resolution, that means on average the building is 20 pixel by 20 pixel. And so certainly if you want to detect the buildings, then you want to make sure at least your target size is 4 or 5 times larger than the pixel size. for the building, right? So if 20, for example, right, 20 meter by 20 meter in general is the object you want to detect, then you want to maybe think about 100 by 100, right? Because the imagery you want to see the patterns, so you need to have the big picture and then see the patterns. Otherwise, the results are not going to be very good. So in general, the target size you can have like 256. Usually is the make sure the number can be divided by 16. So 256, 512, 1024. So depends on the GPU you have, depends on the object size. So you can consider, I mean, normally people use 256 or 512, but make sure you consider the object size you're going to detect. Is the target size in relation already to higher set imagery, or can we produce a full imagery? Good question. We go get to another example that you can pass in just a single big set of imagery without image chips, because we can generate image chips by ourselves. In the first example, because it's non-geo reference imagery, it's already tiled, so we don't need to tile ourselves. But the target size actually is also can handle do all the tiling again. All right, so I think I've answered all the questions. I don't have time to check the YouTube comments, but we can get back later when we have time. So right now I'm just answering the questions on Zoom. All right, so once you have all trained the model, now we can start running the inference, right? So the model here, we have two models, the base model or the final model. So the base, we usually use the base model because you get the best result. Because sometimes for the last model, it might fluctuate a little bit. It might not be the best one. But in this case, the last model may be the best one. So the IOU is the highest, but it's not always the case. So how do we run the inference? You can actually give any RGB JPEG it should be able to do it. For example, for this one, oops. So I'm going to run the inference, for example, in the imagery. I'm cheating here because I'm just using the imagery that we used to train the model for prediction. But in general, you don't have, because I don't prepare other examples. So this is just a demo, right? You can give any other imagery not being used in the training. So here, you basically what we're using is passing to the folder here and then select one of the images. And the index basically, if you look at the images, so let me show you in here, right? So we have all the images, and basically the index is like 1, 2, 3. So for example, we're going to use this one to do the prediction. So the index is number 3. So you can go back to look at any images and then just find out the index, and then you can come back to here to run inference. So this is just specifying all the 5 paths, the images, the ground truth. So background truth is basically the label that we already have. The prediction is the one that we're going to generate. So this is going to be the output. And then the next one is the base part model. So it's the PTF, basically the model checkpoint. And that's it. Now we can just call the function called semantic segmentation and make sure all these parameters are the same as the one that you use to train the model. Because earlier we used, for example, the window target size 512, 3 channels, 2 classes, and the overlap. So when we are doing the model inference, you need to make sure that you have some overlap. Otherwise, when you generate the output, you're going to have some basically hard lines between the pages. So if you have the overlap, then when you merge the result, you will do a more smooth. So you should at least target maybe 25%. So this one right now have 50%. So that means, okay, when you are doing the inference, we're passing a large imagery. It's going to subdivide them into 512, 512. But when you're subdividing, it's like 256 overlap. That means you're basically sliding through 50% overlap, 50%. So in that way, the result will be much better. And then the base size is how many image chips you want to pass into the model all at once. So earlier, you will see we have the base size 16, but there's a lot more images. Right now, we are doing the inference, so it should be much faster. So take a look, less than 1 second. So now we have one imagery. For example, this image size is not 512 by 512. So it's being basically subdividing into 4 image chips. So think about here. This is last imagery. So 512 and then another 512. So it's already done. And then 512 sliding down, 512. So you will see, right, this is why it has 4 windows finished. And then the result should be saved right now here. If you go back to the output folder and then the prediction, and this is the one, right? So this is the imagery that being generated, and this is the outcome from the model. You can also look at basically the comparison, the original one, and then the prediction But we can also generate that one from here. So let me run this one again. And that's it. So original, prediction, and ground truth. So think about here. We went from training the model, evaluate the model, and then run the model, and then see the result. So basically just 4 to 5 lines of code, and that's it. Now we get the result. And of course, it's not perfect because we only train 10 epochs, right? You can train 50. You can increase the IOU to maybe 0.8 or 0.9 if you can. So right now, you will see this one is missing some of the smaller area. It's kind of normal because you're not going to get 100% prediction. If you want to try something else, for example, you can change the index. For example, I will change to 100. So make sure that index, the imagery exists in your data. So this is 100. Then I can run this again, and you can see the result again. Okay. So this is another one. You will see something in the middle here, missing some of those, probably because of the wave and the texture is a little bit different. Again, and just demonstration. You're not going to get perfect align with your ground truth, but this is pretty close in terms of the prediction. And that's it. And that's the kind of the process, the whole process of training the model, running inference, and then evaluate, and then run on a single imagery. But GeoAI also provide another function called segmentation bit. That means you can provide a folder of all the images, and then it's going to run the inference on all of them. So in this case, I have like extract a subset of the data. And then, so in this case, I have 10 images. So 10 samples. You can go back to your data set. You can take a look at the sample data set in there. So in this case, I have 10 images, right? So all I need to do is just to pointing to the folder contain 10 images, and also have a folder that contains 10 masks. And then I'm going to run this same workflow, one line of code. Okay, this is the folder of the images. These are all the predictions, and this is the model, the base model, and then everything else remain the same. And this is just run it. It's going to loop through them automatically. So just a couple seconds. Now I have a prediction for all the result, and that's it. So there's the whole process of training the model, running inference, and then on a single imagery or on a local images for non-geo-reference images. So we can use this workflow, adapt it to any other object detection. It can be buildings, it can be vegetation, it can be water, it can be trees, it can be anything. So the workflow is the same. All you need to just pointing to your input data, and then make sure you have the corresponding labels or the mask, and then that's it. The process is the same. So what you can customize is the model architecture, the encoder, and also the pre-train weight. So by default, it's using, when you train the model, it's using, for example, ImageNet or something else, but you can easily customize it. And then depends on how many channels you have, you can use that to basically apply to do segmentation. So I hope this is much easier for if you have never used it or you have used other deep learning packages, you are very frustrated how to understand all the concept. So I hope the workflow is much simpler and much easier now. And so let me see if there are any questions. If one wants to use satellite or air images through hosting services, is there a way to get training data or test data on the fly using services? I mean, technically, you can. I think right now the package doesn't have that support yet, but technically, you can just read the imagery using remote sensing other packages, for example, raster.io, and then basically what fit into the model is basically just NumPy array tensor. So we can read the data and then convert it to NumPy array and then passing to the model. But right now, you still require the physical files in order to do that. And yeah, that's pretty much it. This is the first example. So we took almost 1 hour to go through the whole process. So I hope you now understand the basics and the concepts. We have 4 more examples. We're going to go much faster because the workflow is the same. The parameters, you can just customize it by this different data set. And so you can try it out on Google Colab. You can follow step by step to go through that. If you have more questions, feel free to ask. And another question, do prediction use the entire target window size or only the central area of the target to eliminate edges? No, it uses the target size. So think about here. When you are running the inference, So it subdivided images into 512 by 512, but it has some overlap, 50% overlap. So it's running 512 by 512, 512 by 512. And then when you have the result, it's going to merge together. So that's why you don't have the cut line between the image pages. So it's basically merged together, and then eventually it looks something like very smooth like in here, because this one is basically a combination of 4 images. So because it's 600, 568 and 565. So as you can think about here, it will be 512 maybe somewhere here, using my mouse somewhere here, right? And then the other one, like 256 overlap, you'll be here, and then another here. And on the right, it's being basically filled by empty data. And then another one maybe somewhere here, 255, 256. So it basically has 4 image pages, and then it's going to run inference on each of those, and then most the final result is a single imagery like what you see here. But you don't have to manually do that by yourself. The model, the package handle everything by itself. The output classes are binary. Is it possible to get the output as probability? Good question. I think in the package I have that, but I didn't expose. This is something I can look into to improve so that you can get the probability. The reason write the math here is because most people just only want math, but you can certainly adjust the probability to get adjust the threshold for something you want. Okay, so that's about the first example about segmentation on non-geospatial data. So the next one we're going to go through is geospatial data, real satellite data. So we're going to use Sentinel-2, and this is a data set available on Zenodo, thanks to the author Xin Ruo for providing this data set. So you can see here, this is Sentinel-2 imagery, 6 bands for each one, and they also have the corresponding mask. So this is basically images covering around images around the globe and different locations. So it's a pretty nice data set, and it's a little bit slow to download it from Zenodo, so I put a copy on Hugging Face, so you can download the data set, and once it's downloaded, you should be able to find it on your here on the left side. If you're still using Google Colab, you should be able to find it under the directory here. And for me, I can show you quickly here is the Sentinel-2. Oops, no, this one, DS Sentinel-2. So it looks like this. So we have the training sync, the training tools. So by the training sync, basically is just the original imagery, 6 bands. And then this is basically the mask. Also, we have something for validation. You will see some of these in here. These are all 6 bands, 10-meter resolution data set. And so what we're going to use is to use this one to train the model. And compared to the previous one, using JPEG, it's already have different pages. So, but for this Sentinel-2 imagery, it's much larger. So if you want to see that, you can open using QGIS, for example. So let me quickly show you here if I can open using QGIS. So, oops. So let me go to here. Let me open a terminal. Okay, QGIS. The reason that we want to create do the tiling because the imagery is much larger. So again, from here, changing, right? So let me drag one of those here, and you can see this is the imagery. You can open it. You can see the spectral band 1, 2, 3, 4, 5, 6, and you can also look at the resolution. It should be 10 meter here, 10 by 10, right? And the size is 868 by 764. So certainly it's a little bit larger than, for example, 255 or 512. So we need to do the tiling because right now it's not, it's the size is kind of similar for each one, but it's not the target size we want. So that's why we still want to apply the tiling to create the image tile. And this is where you create the training data. So if your training data is not tile, then we use this one, export tiles, GeoTIFF tiles batch. So there's a function called export GeoTIFF tiles. If you only have one imagery, let's think about you have a large length imagery or a large Sentinel-2, like couple thousand image pixels by width and by height. But in this case, we have a lot of images. So let me see how many we have in here. Open it again. So we have 63 images in here. So we have basically a folder of all the satellite data. We have a folder for all the image mask. And that's why we use so-called GeoTIFF tiles base. That means we're going to create the tiles based on all the images altogether. So just one line of code and then just run it. You will see the tiles directory. So it's going to generate here this one. So you're going to have the one called tiles, blah, blah, blah. But this one is going to take a while because it has a lot of images. And also the stripe. Stripe, this one, you can change it. The stripe basically means basically the moving window, right? You have 5 by 12, 512 by 512, and the stripe 128 by 128. I guess you can change to 456. That means it's like 50% overlap. So we have a large imagery. You're basically tiling, moving like 512, and then half. 128 is probably a little bit too much, but you can adjust it. So it's going to create all the tiles. You're going to end up with a lot of tiles. So this is the result it's going to generate it, right? Tiles, and then inside you're going to have images, you're going to have masks. So this is exactly the same as the one that we used in the first example. That is already doing the tiling. So this one right now should be a much smaller. It doesn't show up in here, but I don't have QGIS here. So this is where it's already being tiled, and then after that, this is. So the process for the next one is exactly the same as the previous one. So the only extra step is to create the tiles because this one is big remote sensing imagery. And so once you have the tile, then you just change the model. So for example, here I can change to maybe 6 epochs. On Google Colab, only set to 3, but in general, you should have 10, 20, or something like that. So what you're going to look into is look at this IOU or the train loss. So in general, for example, if this keep increasing, that means it still has room for improvement. But for example, I train for 50 epochs. You can see it's like almost converse. I guess you can train maybe 80 epochs. It might increase a little bit more. But in general, the more epochs you have, the slow improvement, the small improvement you're going to get because it's already pretty good. So it's going to take a while to actually to get the base model. But in general, train 20, 30 epochs to see how good it is. And so the GeoAI package allows you to train from the previous checkpoint. That means you can use, if it's not good enough, you can resume the training on the previous training checkpoint so that you can train later. And again, let me stop sharing so that I can open my taskbar so that I think Zoom is going to block my taskbar. Okay, here, IT. Okay, let me share again. So hopefully it will be better right now. I'm 3. Okay, so now I have my taskbar back so I can see this one. I can show you here, right? So this is the tile images and the output is still geospatial data. And you see, right? So this is tiling 512 by 512. And then we have the stripe 128. So the second one would be, if you see this one here, you should have the overlap, right? 128. So look at this. So it's moving basically to the right. But I think you can just change the stripe to 256. It should be fine. And we have done with the training, right? So we have trained 6 epochs. Now we evaluate the model. So this is what you see. In general, in the first couple epochs, you will see the IOU or the loss kind of fluctuate quite a lot. It's probably normal. As I mentioned in the analysis I gave you earlier, right? Imagine from the mountain top go to the bottom, there are multiple routes. So you kind of basically wandering around. Eventually, towards the end, you will know like this is route I need to go. At the beginning, there you might be presented with too many options. So what we need to go is basically decrease the loss. But in the meantime, also need to look at the validation loss because you can train a model that's perfect model for your training data. And then when you apply to the real world data, it doesn't perform very well. That means it might be overfitting to your own data. And then it doesn't generalize well to the validation. So this is why you always need to have a validation to make sure that the model can be generalized. And so this is the first one I'm going to show you. It should be decreasing. So the more you train, the better you're going to see it's going to keep decreasing and getting smaller and smaller. And the IOE becomes better and better. And once you train the model, and then the process is the same, right? So we can point to the data that we have, different from the previous example. Oh, it's the same example, segmentation batch, okay? Because we have the validation, we have a lot of validation thing here, for example, of this validation. We also have the tools, and all need is one line code, segmentation batch. It's going to loop through all the 31 images and take a look how fast it is. And within a couple of seconds, now we have the result. So the result is being saved here in the predictions. So we have prints all the inference for all the data. So it's pretty nice. It's very fast and it's very simple. Now you understand like how to actually train the model and apply to the inference. And lastly, you can check the result. So for example, here, this is for one of the validation images from the data here, right? So the validation scene, we have multiple images here. I'm just going to select one of those. And then you can use this function plot prediction comparison, right? So this is the image chips, and not the image chips, it's the original imagery. This is our model prediction, and this is the ground truth. So the ground truth come from here, validation truth, right? And take a look. It's pretty good, right? We only trained for 6 epochs. The result is pretty decent. Of course, there are some minor things if you look closely, but you can change it to other data set. For example, I can change to this one. So I have 31 images. You can change to any of those, and you can see the results, see how good it performs. And for this one, we detect a little bit more than this one. So this is a tricky issue because in remote sensing data, we have a lot of clouds. So cloud going to generate the shadows. And so in this case, the model doesn't really distinguish very well between the cloud shadow and also the real water. And that's why you see something like this. So you can certainly have better training data and then train a little bit longer. Also, you can have a model that's specifically used to distinguish between water and shadows. Then you might get better result. But this is something that certainly you should keep in mind that the model is not going to be perfect. There are going to be lots of confusions. Even for us human, sometimes we don't distinguish them very well. But the nice thing about this is you can train the model, it's just pointing to the entire folder of images, and then it's going to get all the results all at once. Pretty cool. So that's the second example so far. And by now, we have trained the model, but think about here, we have this nice training data, we have this nice model, but I want to apply to do water mapping for my own area for a real Sentinel-2 data. How can we do that? So I have another example here showing you how to download the data and then how to create the data and then prepare the data so they can use this your own data to use the model that we trained to apply on your own data. So for this one, I'm going to use diff map, and I'm also going to set up the t-tiler so that we can visualize the interactive map. So for this case, for example, okay, I create a leaf map, and then I want to find some data. So leaf map already have some functionality allows you to search the data interactively. So this in the area, for example, here in Minnesota. So we can zoom out here, for example. It can do it for any location around the globe. So for this particular location, I want to find some data. So for example, I can just simply draw a rectangle, and then somewhere, okay, let's see, I want to map the surface water body in this area in the latest available data. So how can I do that? Okay, I draw a rectangle and then just click search, and that's it. So I'm going to search the entire Sentinel-2 catalog, and you're going to find, for example, this is the footprint being returned, so intersecting with my area of interest. You see here at the bottom here showing you some of the basic information. So for this particular image scene, there are multiple images. So you take a look at here, we have a lot of images starting, for example, from beginning to the end, and we can select the first one, for example, September the 3rd, right? So only maybe a week ago, and then you can just click this display button. You will be able to display the imagery on the fly. So we haven't downloaded the images yet. Right now, we're just showing you how to visualize data. Of course, this one doesn't look good. It has a lot of cloud. And maybe let's try another one. August 31st, click display again. And hopefully we're getting a better imagery. Okay, this one looks, I think, certainly much better. So there's still some clouds, but it's pretty decent. So for example, for the area of interest, it's very clear, so there's no cloud. And this is how you can source the data using the package, using either LeafMap or GMap. And you can, there are AWS data, Plenty Computer, or other third parties. You can try it out. And then you can either also specify the date if you want to, and then the end date, and you can specify what bank you want to visualize. So this is how you source the data for your own area of interest. And we will need basically the bounding box. So this is the bounding box that we draw earlier. So if you want to get, for example, the bounding box that you draw, certain imagery, you can use m.ri bounds. You can get the bounding box as a coordinates. So we can use this one later to actually do the source the data programmatically. Also, you can show basically all the data. So for this source, you will see it's going to return as a data frame, and it's going to show you, for example, all the images. So the data frame shows you all the images available. You can also run this one, the stack item. So this is the item specifically we showed it on the map. So you see here, this is the one that we showed earlier, and we have all the URL, the HTTP URL. So this is the one that we use to visualize. I'm going to show you how to download the data automatically, but you will see it contains a lot of links inside there. So in order to download the data, we can do it automatically. So we're going to use the AMN84, the endpoint, and we're going to use the Sentinel-2. And this is the bounding box that I get from the previous step. You are welcome to find other areas. So for example, if you're working on another location, for example, I want to do maybe water mapping in Chicago or somewhere, you're welcome to do that. You just draw a rectangle here, and then you just run this print the user ROI. Oops. Not here. I think it's the first one here. This one. So run it. You will get this one, and then just paste this one to the code block here, and then you'll be able to actually source the data. So we can see here, we're going to basically use the stack catalog to source the data. And this one, because we specify August 15th to August 31st, you can customize this one. So it depends on the time they're interested in and the region. So basically you figure out the time, the spatial location, and also the time. Then we can pass this one into the function to source the data. We also limit the data to cloud cover less than 10%. So because we are doing the detection, we want good quality images, and you will see we return one image. So this is the one, exactly the one that we saw you earlier in the visualization. So this is the data. You can see all the links, and 1, 0, 1, 2, 3, all the way to 7. So, and then if you want a different way of visualizing the data, you can also return it as a GDF. So GDF basically means get the geo data frame. And again, so this is the data pointing to the imagery. You can also get the assets. If you want to, you're going to get all the links. So this is how we automatically download the data. So you see, if you click the link, it's open a dialog asking you to save this one to a computer. So you can either download the data manually, or the better way would be download the data automatically. So here, we're going to use these 6 banks because the model we trained earlier has 6 banks, 10-meter resolution. So we're going to use the same data set in here. And so blue, green, red, near infrared, and then shortwave infrared. And we have these 6 links, and then pretty much it's just going to download it automatically. I already downloaded it, so I already have the imagery on my local, on my computer. And so you should have this B2, 3, 4, 5, 8, 11, and 12. And then what we need to do is to stack the banks together. And in Google Colab, you might need to run this one uncommon. Otherwise, if we download a sample data set from my Hugging Face, so it's a much smaller one, it's not a full image sync, and let's see visualize the data. So you see, so this is the imagery that we have. We downloaded 6 individual bands, and we combine them as a 6 bands, and this is what you see, 4, 3, 2, 1, right? So this is just the first color composite. You're welcome to change it maybe to 3, 2, 1. That will be the natural color composite. So it's going to be, this is a little bit dark. And if this case, you can change this value max to a smaller number. So basically stretch, rescale the value. So this should be a little bit brighter. Okay, still a little bit too dark. Let me change to 2000. So basically the package provide a way for you to actually visualize the data. So this is the imagery right now stored locally or on Google Colab. So we have this imagery. Now we are ready to run inference. So we from the training the model, and then we get our own data. So for the training the model, you can use other people's data. But for inference, you want to run it on your own data. So this is the real use case that we have. So we have this imagery. Now we can run the inference. Again, I'm specifying where is the model. And then instead of segmentation bit, right now we only have one imagery. So we manage this single imagery and just run it. It's going to basically subdivide the images into 512 by 512. And right now we're using overlay 256. So 256 basically moving window 50%, 50% over that. And everything else remain the same. So we have 6 channels, we have 2 classes, and we use the same model architecture, base size 32. If you have a smaller GPU, you change the base size to a smaller one, and that's it. So it take maybe a minute or two. Think about here, this imagery is pretty big. It's a decent size. If I go back to my imagery here, I have this Sentinel-2. This one is 1.3 gigabyte. So it's a pretty big imagery. If you try to run this one on Google Colab, I think it will exceed the memory. It may not work. I have a larger GPU, so it works fine. And now let's see the result. Okay, with the raster. So this is the result is the mask. And take a look. So we go from training the model using other people's data to run the inference on our own data that we downloaded from AWS. This one right now is loading. It's a little bit slow, but it's pretty nice. So we extract the water body using the train model for the entire Sentinel to sync. So imagine you can download a bunch of those images, and then you can just using this workflow to train your own model pretty quickly. Okay, so this is the whole process, like end to end, from training to run inference, showing the result, and then you can running that on our own data. There's the last step here, empty case. So that means is if you're running on Google Colab, so on the right here, okay, right now I'm got disconnected. So you will see like the GPU spike. If it is exceeded, then you might need to empty the cache. Empty the cache basically just remove all the stuff from the GPU and then become empty. So I can remove it. So once you remove it, you cannot run that. You can run it again. It's going to load the model back to the GPU. Okay, and that's it. That's about running the image segmentation on real remote sensing data. There are a couple other questions. Recommend using 50% over that using tiling. Usually 25% is fine. So at least 25%, I think you should be fine. Depends on the image size. So the larger the object size, the more overlap we want to have. The smaller the image size, then you can have smaller overlap. But in general, 25%. Or for example, if your target size is 512, then your stripe would be 386. So that means you're moving from 380, 75%, 75%, 75%. You only have 25% overlap. What can we do using on glaciers? Users have set imagery, you have the glacier mask, and the workflow is the same. Just think about the water is your glacier. If you already have the mask, you have the data, then you can do that. If you don't have the data, then you need to create the training data, certainly. So this is how you can use that to do other glacial mapping. All right, so that's the real workflow for doing remote sensing data. And we only have half an hour, so I'm going to go quickly for another 3 examples. So you can, actually I have 4 examples anyway. So each one only have less than a couple minutes. So I'm going to go quickly. So the next one is doing the, I only have 3 actually. So the surface water mapping using area imagery. So this is much higher resolution, right? So from the Sentinel to 10 meter, right now we're doing 1 meter resolution. So same thing, I provide some sample data here. You can download it in, you can take a look at what the data provides. So this is a 4-band RGB and also near infrared. So it's a USDA NAP imagery, National Agricultural Image Program. If you want to learn more, if you're outside the US, you're not familiar, you can look at the USDA's website. I don't have time to get into the details. So basically it's a area imagery, 4-band, 1 meter resolution, or sometimes like 60 centimeter resolution, pretty high. So you can see here, I downloaded some sample examples, and then you can visualize the sample data that I have. So if I run this one, you should be able to see the imagery that I have. And so I visualize the mask here on top of the imagery. So I have the 1 meter resolution, USDA name imagery, pretty high, and I also have the mask. So the mask is the one that I created by myself, and this is the one that actually not super accurate. It's like classified using Google Sensing, pixel based, and then I just use this one for training. So think about the training data is not super high quality, but it still do a decent job later. So we basically what we have right now is these two images, okay? The aerial imagery and then the mask. Then I want to train the model and then to apply the model to do mapping on another imagery. So these are the two different images, okay? So they are different. So let me just make sure that you verify that, okay? So this one is to the, I think, to the bottom of the other one here. So this is the imagery that we used to do the training, and I use this one to do the prediction. So same thing, I'm going to just create the training, export GeoTIFF tiles. It's the same process. So the strike here is 256. Like I said, I can maybe 386. It's fine as well. Or 384, 75%. But 256 is maybe a little bit too much. And it's going to subdivide all the images and then creating all the image tiles. So let me show you one more here again, right? I'm going to open my imagery. So right now it's under the name imagery. So we have all the images here. So it's subdividing my entire images into 512 by 512. And we also have the corresponding label. So right now these are all black because it doesn't show up, but it's basically just the corresponding image and mask. And then we're going to change the segmentation model. So think about here, the same function, like the same one function to rule it all, right? You don't need to construct different, you can customize the model architecture in the encoder, but other than that, this one, the only thing you need to change is the number of channels, right? So we have 4 channels, RGB and near infrared, and the number of classes is 2. So by default, it's just 2, but you can specify it if you want to. So because it's running, so right now it doesn't work very well. But you can just use the default one, and the base size is 8. So we are feeding 8 images into the model all at once. So I only train for 3 epochs. I usually train a little bit more. For example, I train maybe 6 or something like that. It's going to take a little bit longer, and this is where you can see the GPU usage. So pay attention to the one that you see on Google Colab. Right now, I'm using 2 GPU, and once it's done training, this one will drop to close to 0. So let's wait for it to finish the training. Let me see if any other questions. If a full satellite imagery is delivered in various GeoTIFF, do you recommend mosaicing them before tiling? No. So all you need to do is just follow the example. In the second example I show, you can point the program to all your images. So the example that I showed you earlier, that one is exactly your use case. So I have the Sentinel-2, I have the images in here, the training, right? It's a bunch of images. It's just a folder. So you don't do the mosaicing, it's unnecessary. Just pointing your input to this one, and it should be done easily. And okay, so now you see the GPU is less usage is done. Now I can plot the inference. Okay, so this one is not very good. You probably need to train more epochs because it's like very good, and all of a sudden it decreased because it depends on the randomly selected images used to feed the training. So if this is the case, you might want to train a little bit more, but it's fine because we saved the base model. Although the final model is like not very good, the base model is pretty high. So we can use the base model just to run the inference. But like I said, train more until you see the train is like overall, it's like getting better and better. So now we can run the inference on the imagery. So for this one, I have just one imagery, but it's a pretty big one. So it's going to subdivide it one into smaller tiles, and then it's going to run the inference. And at the end, it's going to merge all the results all together. So this one is taking a little bit longer, but you can change the parameters to make smaller overlap. So it should run a little bit faster. You will be able to see the results shortly. And you value the model. Oh, sorry. I think I this wrong. I already finished the evaluation. It's go to the inference, not somehow the cursor run back to that. So this is the model, okay? And then we can run the inference. The inference should be much faster, okay? So it's going to subdivide the image into 280 tiles, and then just run, see the result, and that's it. So this is our outcome. So we train the model on another imagery, on another area, and then we just run the prediction on another imagery and take a look. Like I said, it's not going to be perfect. It's going to have same issues like shadow and other stuff. We need to find other ways to actually improve it. But this is the easiest way that you can train the model on a high resolution imagery and then apply it to another data. Like I said, train more epochs, get better results. For the save time, I don't have time to do all that. And once you get the raster mask, sometimes you might want to extract to vector. So for this one, I'm going to call this function called raster to vector, and then I can add some geometry properties. The reason for that is like, okay, so this is the result that we have, and we have some of the result, but the result is not very good. For example, I have some of these shadows. Look at this. These are some of the like false positive, and clearly these are the shadows. And for this one, you see the smaller size, so we can actually set a threshold. And also this one is very long, elongated, and we can add geometry properties. And let me show you the geometry properties they convert to vector. But right now, if you hover my mouse here on this detection, it will show you all the geometry, right? So for this one, you can see the elongation is 13.9, so almost 14. That means the height is 14 times of the width. So in general, the water body doesn't look like that. So this one probably is just too much. Also, you now see we set a minimum size, and all those smaller objects have been removed compared to this one. So the package have some of those functionality, allows you to quickly add the geometry properties, and then you can use GeoPanda, for example. Okay, look at this. All the objects are pretty kind of similar to like circle, and this one's pretty big. So this is the one that's kind of an outlier, and then you can just filter them out. Once you filter them out, you see now we have 70. We down from 73 to 72. So that means you can remove. So this is some of the basically the post-processing step that you can use to improve the result. So now we have a much better result. So it's converted from raster to vector now. So we don't really have all those pixelated result. It looks so much better. And also you can create a split map to actually compare the results side by side, right? So right now we have this red color, and these are all the water body. Like I said, forget about water body. It can be anything. It can be buildings, it can be roads, it can be trees, it can be agriculture, it can be glacier, it can be infrastructure, anything. So all you need is just your imagery and then your label, your mask, and that's it. Okay, so there's the example. And so next, we have another example for building detection. I only have 20 minutes, so I need to go very quickly. And the building detection is the same, right? So but the only difference is the label data is for buildings, not for water. So I have sample data here, and then I'm going to show you quickly what it looks like. So this is the building data that I have, okay? So the imagery is from the USDA 1 meter resolution. And then the building is from Overture Maps. I have other examples showing you how to download the data. If you're interested in it, you can check out the notebook, how to download data for your area. So the building data is at the global scale. The name image is just for the US. So you can customize to your own area. So right now, I only use this sample area. So think about here. This is the imagery they have. This is the building footprint that I have. And all I wanted to use this imagery to train the model. So how do we do that? And this is the imagery we want used to do the inference, so do the segmentation. Imagine you don't have building for this area. But one thing you need to keep in mind is that this one pretty nice, and all the buildings are kind of same similar size, although we have some bigger one here, but we have some large modular complex in here. Imagine the model going to not generalize very well because the model is not trained on large buildings, so it might not generalize very well. But this is what we have. And then we're going to create the training data, the same process, export GeoTIFF tiles. So instead of export GeoTIFF tiles batch, right? So if you have a local image, set of images in a folder, then you want to use the batch more. For this one, we only have one imagery, and then we have one vector data. And for the in-class data, this one is basically the GeoJSON, the polygon to the data. So you can point to just a single vector data, or you can point to a raster mask. It's vector, either vector or raster. It doesn't matter. If this vector is being converted to raster. So this is where you specify your imagery and then your label, and that's it. So here we use the 512 and then straight size bar for radius. So this one we use 0. But if you're doing row detection, so think about here, you have a row, it's just one line, then you might need to do a buffer because otherwise the line is too tiny. It might not, the label might not work very well. For buildings, we want a precise building outline, so we don't really need to do buffer. But for other like linear features, usually you want to have a buffer so that your label is not empty, not a single line. It might buffer a little bit, okay? And then this is train the same model, the same whole process, train the model. So for this one, we only train for 3 epochs. You need to train a little bit more. So for example, I train for 100 epochs. You see the increase from 0.91 or something to 0.97. But in general, you see after 20 epochs, it's pretty decent. So if you can train 20 epochs, that's pretty good. And for this one, right now, the score is only like 0.58. It's not good enough. So the result is not going to be super good, but we don't have time, so I'm just going to quickly show you the result. Once you train the model, now I can just run the inference. As you can see here, the same workflow, segmentation, and then just output. One thing is different from the water detection we did earlier is this orthogonalize function. That means it's going to rectangularize all your buildings, and then when you get the geometric properties, now we can visualize the building. Of course, here, you're going to miss a lot of buildings because we don't train enough, but yeah, it's okay. Some of the buildings are not regularized very well because it's a little bit more complicated. So the algorithm still have room for improvement. The rectangularization is actually a quite complicated problem. There's no there are some packages out there that can do some of the things, but it does not work in all cases. So if you know a better algorithm like building rectangularization, feel free to let me know. Happy to integrate. But like I said, the result doesn't look very good because the score is not very high. So if you train 20 epochs, it should be much, much better. Okay? And then you can do the filtering. For example, I only want to building larger than 50, more than 50 square meters. Then you will remove some of those tiny ones. So now we have much cleaner one result in here. And you can also create a split map to actually see the result here. Not bad, but not super great because it's just because the limitation of the training data and the limited number of epochs that we have. And that's it. So this is the same workflow that we apply to do the building detection, the same workflow. And then we have some additional functions to rectangularize the buildings and then can save the result. So this is one use case. The next one is about integrating LiDAR data. So we can use the name imagery. The LiDAR data is like high above ground data set. So the data set is from Planet Computer. Again, we don't have time to go through the detail, but you can check out the notebook how to download data from Planet Computer. To save time, I already download some of this sample data. I want to show you what it looks like. So this is the building we have, and we have the area imagery. And so look at this. So this is the area near in Las Vegas. So the imagery from USDA, and the building is from Overture Maps. And you can see it's pretty dense buildings. You can turn the layer on and off, right? And so in this region, for example, it's a fast growing. Not all the buildings have been mapped yet. And if you want to detect the new buildings, this might be helpful. So this is the imagery. We also have the height above ground. That means like the building height. So in general, building is going to have some height, right? So we visualize this one using leaf map, and you can see, right? So if you overlay the buildings on top of the height above ground, so you should expect to see the brown color basically is the have height, the taller buildings, and if you overlay this one, right? So this is going to be very helpful because earlier in the model without the height above ground, the result is not very good because there are lots of like parking lots or maybe some shadows being detected as buildings. But if we have the height above ground, So you can basically assume that there must be some height. So if there's a building or like detected along the road, then it's not going to be correct because it doesn't have the height. So we can use this one to help us improve the model accuracy. And this is it. So right now, our data set is an aerial imagery, 1 meter resolution, a high above ground data, 1 meter resolution, and we have a vector data set. So we have 3 data sets. And then in order to fit the model, we need to create image chips. So now we need to basically merge, stack the LiDAR and the aerial imagery together in the same imagery so that you can create an image chip that have multiple bands. So what we're doing here is to call this function. I might need to run this one. Sometimes I have some issues, GDAL and project installation. So, and the stack band is very simple. We have this aerial imagery. We have the LiDAR high above ground. And then we're going to basically stack them and then provide a data set. So you see here, it's going to basically merge the four band aerial imagery with the 1 band LiDAR data, and then combine them together as a single imagery. And this one is going to be pretty big, so you can see 4,000, something like that. So I'm going to merge them together and then just going to have the output. So it's done. And now I also need to stack the testing data set because we have the training, we have the testing. So the byte basically is just like integer 8 to 56. You can change the float number. The file size is going to be much larger. So if you have a small GPU, then you can just doing this one. So the downside is that the elevation is going to be changed from, for example, float to integer, but it's still fine. It's going so much better than just using the aerial imagery itself. Okay, so once we merge the data, now we have the input data, and then we have the 5 band imagery, and then the building. The 5 band basically is 4 band net imagery, and then 1 band the height above ground. Then we can basically create the training data. So this one might take some time. You will see here we have the type size 1024, and so the reason why we increase this one is maybe there's some larger buildings, so we want to increase the type size, and the strike is 768. That means 25% overlap. So 1024, and then move 7068, 1024. And we use this one to actually create the data. It takes a while because the image, you see here, we have a lot of buildings and the size is pretty big. So this one, we take some time to create the image chips. But once you have the image chips, the workflow is exactly the same. And we have 10 more minutes. I think we'll be able to finish it once it is finished training. Let me take a look at the questions. Any tips on how many labels to create and fine-tune a model to identify buildings in Africa? You need to have many buildings, right? Depends on the region. The building pattern is different. So you need to make sure that the building labels can cover different scenarios, like some like dense buildings, not so dense buildings, and also the structure. So you need to, you can utilize the overture maps. It has like global buildings. So that's the base data set that you can have. As I said, you are welcome to check out the tutorial here. I think I have the plenty download data. This one should show you how to download the building data from overture maps for any location around the globe. And then all you need to just find the imagery about that. And how about installing GeoAI on MacBook like September GPU? Yes, it's the same. So you can install a package. So the package should support the what's they call MSP, the MacBook GPU as well. If you run into issue, feel free to submit a pull issue on GitHub. But I think I already support the MacBook GPU. And okay, still running. That's a little bit slow. What else? Let me see here. And how well do the model work with SAR imagery? You just combine the SAR imagery like 3 bands, right? So basically, you only have 1 band. You put in as 3 bands, then it should work as well. So just put in as 3 bands. But it's not trained on SAR data, so it might not work very well. I don't know. I need to basically look into the example. Do you suggest converting TIFF to COG files if you're using your own multispectral imagery? No, you don't have to. The COG file I have on Hugging Face is just to make it easier to visualize the data on the fly. Cloud optimized GeoTIFF is better for visualization. But if you already have the TIFF file, you don't have to. Just pointing to the data and then create the image chips. It works as well. Okay, so now it's done. Now we can run the inference. It's going to basically or create the image chips. So now it's actually running the training. That image chips took a while. And so this one, how many epochs we have? We only have 3 epochs. Okay, this is sweet. And so for this one, because we have the base size much larger, so we only, okay, it's done. Now we run the model. Okay, again, it's not super good. Like I said, train 20 epochs, the result will be so much better. And you can see this one, it'll fluctuate a little bit, but overall, it's increasing. And lastly, this one, the model segmentation, and it's going to subdivide your images into image tiles, and that's it. Once you have the result, then we can visualize the result. So, all right, done. Now this visualize. So this is going to be much better than just using the array imagery alone, because we incorporate high above ground. So you have information incorporate. So now take a look. We have this applying this new imagery. So all the black color is basically the building detection. Of course, you're going to have some still some false positive, and it's normal because we didn't train a whole lot of time, but it's pretty decent. So you can see here all the results, and then we can just vectorize the mask. And this one we have 5,478 features, so it's a lot more, and hopefully it'll be done quickly. And it's the same process as the previous one. So after you get the result, you add some geometry properties, and then you can use the geometry properties to filter the results. And hopefully it's done. And then, so 3,918 images. Now we can visualize the vector data. See? Take a look. So we also have the color range. So that means the brown is the color to the right. That means it's the larger the building. So it's using the building size. Of course, this one is using just the semantic segmentation. So some of the buildings that are being merged together, or you can use the instance segmentation to have a different ID for each individual building. But in general, this is how you use to incorporate the data. So all you need is just combine the input data, then you should be able to train your model. And again, we can filter building, remove some of the larger buildings, and then create a split map. Like I said, the process is the same. So you can create a map just to visualize the building yourself. Again, this is not the state-of-the-art model, but the process is much simpler. So you can customize the model, improve the training. Eventually, you will get much better result. All right. So last example, solar panel. We have 5 minutes, so we're going to go quickly. Like I said, the process is the same. So I already have some simple data there for you. And this is the air imagery. I also created the training data. So this one I created manually, so it took me a while. Like I said, my priority is not to create all the pre-trained model that you can utilize directly. I don't have the resources and the time to create all the training data, but the workflow, you can adapt this to training all data. So I did create this one manually. So this is pretty decent size. Not decent size, it's small, but the quality is pretty good. And then I'm going to apply this one on another area to detect the solar panels. Again, I'm going to create a training data. So one imagery, one vector data, and then create the image tiles. Once you have the image tiles, then just train the model. So for this one, I'm going to train, for example, 8 epochs. It might take a couple minutes. And then you can run the inference, train the model. It's the same whole process. So hopefully this notebook get you started. So now you know kind of the process, how to get started with deep learning. Super easy. There are not a lot of technical terms. All you need is just coding some functions, prepare the data, and then create the image chips, train the model, run the inference, evaluate the model, run the inference, and then plot the result or do some post-processing. That's it. So should be pretty easy for you to try out and get started. How many epochs is this? Oh, I actually trained 30 epochs, so it's going to take a while. Anyway, so that's all for today. We have 5 minutes. If you have any questions, feel free to ask. And I have a final poll that I want to ask this for you to provide any feedback or any topic you want to see in the next webinar. Oops. Yeah, I cannot share or share the result. Stop. And Yeah, always. Or go back. So I have a poll there. I want you to provide the feedback. So basically, what topic you want me to cover, and any feedback you want to provide, or anything we can improve, anything you like, anything you don't like. So hopefully, we're going to have this continuing in the next couple of months. So we have a lot more things to cover. For example, land cover classification, regression, prediction, and some other large foundation models. So I recommend that you bookmark the start the GitHub repo. So all this update will be from here. So if you want to get the latest update, please bookmark it. And I hope to see you in the next video. So this workshop is being recorded. I will upload the video to YouTube later. And if you have any questions, the best way is to ask questions. If you have finding issues, is to post issues on GitHub. And or if you want to contribute, you're very welcome to submit a pull request. And so I hope if you are new to this package, I hope it convinces you now that you can use this one to easily do some deep learning without having a deep knowledge about all the technical terms. And we continue to develop the package for the rest of the year, and looking forward to seeing you guys how you use the package to apply your knowledge to make an impact. Okay, that's all for today. And let me see here. Yeah, please fill out the feedback survey, and I would really appreciate it. So let me see, it's done. The last one here. Is it finished? Okay, so it's done. So let me quickly plot the evaluation. And this is very interesting. The last epoch actually dropped a lot, but we have the base model. It should be pretty decent. So the IOU is around 0.8, not bad. So now we can just do the segmentation on imagery, and then just visualize the data and just do the segmentation, create the result. Again, it's the same process. It might not be super good because the data set is super small, but take a look. It detects some of those buildings. It works. It's just not perfect. So you can improve it, try it to your other applications. Okay, so we have only 2 minutes. If any other questions, feel free to ask. I will try to answer questions here. But if not, you can ask the questions here on the GitHub discussion. So if you have questions, ask the question here. If you find any bugs, report the issue here. Or if you want to contribute, just submit a pull request here. And that's all I want to cover in today's workshop. And I hope you find it useful, and looking forward to seeing you maybe in 2 weeks. I haven't decided the topic yet, but I'm still working on some of these features. But stay tuned on social media, on LinkedIn or Twitter, and I will announce it maybe sometime next week once I figured out what to cover next week. Okay, thank you very much, everyone. Thank you also on YouTube. I didn't have time to look at the questions on YouTube, but I will look into that and then incorporate some of the feedback into the package in the future. And thank you, everyone. I hope you enjoy the rest of the day. And I have a doctor appointment that I need to go at 12 p.m. So I don't have time to stay longer here. And that's all for today. See you next time. Take care. Bye-bye. And let me stop here.